erase the blackboard. Back, the previous speaker just mentioned a problem about a Superman going down, and amazingly enough, that's the problem that I chose. So, seriously, it is. Well, maybe there are a lot of problems about a Superman, but, well, let me first introduce myself. My name is Anton Capley, and you can reach me at AntonK@UChicago. And as you can see, I have some accents, so if you don't understand something, feel free to ask, and I'll try my best to make myself clear. So the problem is from chapter 2. Yeah, this is Physics 121, so make sure you're in the correct room. So it's chapter 2, problem 79. It's marked as a difficult problem, a challenge problem, but I just want to show you that there's nothing difficult about it. And so the problem is, you're doing a science project, so you're going on top of the Empire State Building, which height is given as, let's see what's the height, 320 meters. And for a science project, you're dropping a watermelon from this building. And it so happens that when you drop a watermelon, the Superman is passing by, and the Superman is heading straight down. That would be a Superman, right at the instant when you throw it. And what we know is that the Superman is moving with a constant velocity, which is 35 meters per second. So let's call it V Superman is 35 meters per second. And this notation means that this velocity doesn't change over the course of the problem. So we're asked to find the velocity of the watermelon by the time when it reaches the Superman. So let's call it velocity of the watermelon at the time of encounter. So is the physics of the problem clear? What we need to find? Yes?
Do they start at the same time?
Yes. So basically, you can think of it as if you're throwing this watermelon right when the Superman flies by you. So you see the Superman flying and you're releasing your watermelon.
But why wouldn't he catch the watermelon right away?
I don't know. I guess we should address the authors of the textbook.
So you want to know the second time they cast it next to each other.
Yeah, well, actually one of the questions I wanted to ask how many solutions this problem has, and you already answered. The problem has 2 solutions, and the first one is trivial. It's at time equals 0. They're at the same altitude, so it's the time of encounter is the initial time. And so the first answer is V equals 0. We're just releasing the watermelon. So let's find the other solution. So the textbook... what's their comment?
How much time it takes for the watermelon to catch up the Superman?
Well, we can find that also. Well, in fact, we will find it in order to determine the velocity of the watermelon when it passes the Superman a second time, which is what we need to find. So the book suggests that the first thing that we do is label our axis. So let's call this a y-axis, and it will be pointing straight up. And let's take a 0 at the ground level, which is a quite natural choice. And so let's consider those 2 bodies separately. So this will be related to the watermelon, and this will be related to the Superman. The motion of the watermelon is the constant acceleration motion, as our book instructs. So let's recall that the formula for this motion is for position. It's initial position plus initial velocity times time plus acceleration times t squared over 2. For Superman, a similar formula. Superman is moving with a constant velocity, so the formula is actually simpler. It's initial velocity, it's initial position plus constant velocity of the Superman times time. So if we want to apply this to our problems, we can use instead of y0 height, let's call this h. One of the things I want to teach you is not to plug in numbers from the beginning. So you should be labeling everything with some Latin letter, and you'll see why it is a good idea. So if we write this equation, we'll start at height h, then the initial velocity of the watermelon is 0 because we're just releasing it. So it's plus 0 plus. So the acceleration, as our book instructs us to do, is minus g for free-falling body with our choice of axis. So this will become minus g t squared over 2. For a Superman, a similar formula yields. So initial altitude is again h, and the velocity of the Superman is constant, and it's, yes?
Are these two y's equal?
Right now, they're not, but we will make them so because we would like to find a point where those two bodies will be at the same altitude. So we will set equal this altitude and this altitude, which will allow us to find the time when this happens. And when we know the time, we will be able to find anything else we need. So the velocity is minus s times t. This is a generic v. So in order to find the time when those two bodies will be at the same altitude, we can just equalize those two equations. And so what we have, h minus gt squared over 2 is h minus v Superman t. And you can see that you can cancel out h right away because it's on the both sides of the equation. And here you see that we can read off the first solution right away. We have t on the left-hand side and on the right-hand side, so we can cancel it. But when we cancel it, we have to write down that there is the first solution, t1 equals 0. Now we divide by h, and we have gt over 2 is vs, the constant velocity of the Superman. So this gives us the time of encounter to be 2 times the velocity of the Superman divided by g. So here you may have a temptation to plug in numbers because we already know everything. But you shouldn't do this yet because what we need to find at the end of the day is the velocity of the watermelon at this time of encounter. And if we recall the formula from the textbook, velocity of a watermelon is given the initial velocity of the watermelon plus acceleration times time, and initial velocity is 0, so it's 0 minus gt encounter. And if we plug this t encounter, we can see that g will cancel out very conveniently. So the answer is 2 times the velocity of the Superman, which is 35 meters per second. So we have 70 meters per second. So that is the answer to the problem. If, on the other hand, you try to plug in the numbers here, you would probably use g equals 9.8, which is what the book suggests, and you would plug it into your calculator and you would round off. And then you will multiply by this g again here, and your answer won't be exact. You will have something like 69 point something, and you don't want to lose this for no reason. Is the time up?
So,
I thought it was very good to include the point about